Okay. Afternoon, everyone. So we'll just get started on this. People are still joining. So there we go. So we're getting now into a more interesting part of power supplies, or a technique that can be used in power supplies, but can also be used in other areas as well, and is a big favourite in integrated circuit design, which is switched capacitance, which comes from, it's sort of similar in many ways to the switched inductance stuff that we've been looking at, but obviously uses capacitances. So we'll talk a bit about that, and we'll look at how switched capacitance systems can be used for power supplies, and quite interesting power supply configurations. How we can then emulate resistances with switched capacitances, and how that then allows some interesting design techniques in particularly integrated systems to be put forward, particularly in terms of tunable filters. So it's all starting to join together. Just get rid of me so I'm not in the way. Okay, so we've looked at buck and boost converters, and sorry, I was just making sure everything was recording. I don't want to have to do this twice. Seems to be. And they make use of inductors to store the energy and switch between voltages and shuffle energy through the system. In principle, we could use a capacitor because that can store energy as well, and we'll look at how we can possibly do that. So they're not as popular as inductor-based systems because they tend to be good at generating voltages rather than currents. But as you can see here, they can be good for generating negative supply rails in systems. So if you've got a battery powered system which is running on, say, Norton 1.5 volts off a single battery, then to generate a negative supply rail we can use a capacitance based system to generate a minus 1.5 volt supply, giving us plus and minus 1.5 volts. We can boost the voltage as well, but we have a choice of techniques. We can either use the inductive regulators to boost voltage, or we can use the capacitance one as well, but capacitance ones tend to be a bit limited on the amount of current they can supply, but they're good at generating very high voltages. And they can be self-starting, which is useful in certain areas. Starting up of circuits is always quite an interesting problem, because if they've got no power to start with, how do you get them to sort of start switching? Which is an interesting problem, particularly in the world of self-powered systems. When they've gone flat, how do we turn them on again? If they're being powered from the thing that they're trying to generate the voltage from, it's sort of pulling themselves up by their own bootstraps in some ways. But capacitance systems can be configured to self-start. In other words, as soon as there's enough voltage applied to them, the switching can start automatically without any sort of timers and everything else going on, as long as there's an AC voltage coming into it. Anyway, we'll look at that, and hopefully that will become a bit more apparent why that might be interesting as we discuss this. An extension of this idea of charge pumps, which we'll talk about, is, as I alluded to earlier, is exploited in IC design, where we can start to simulate resistors by putting a capacitor in the circuit and switching the capacitance in and out of the circuit very quickly. And this becomes really interesting for frequency dependent circuits, because we can then control whole systems just by changing the frequency of an oscillator that's controlling it. And the reason why that's interesting will also hopefully become apparent as we go forward as well. But it's an interesting interesting technique that we need to look at. So the simple idea, the idea behind all of these things really, is that if we have two capacitors and we happen to have them in parallel, like in this configuration here, and we charge them up, if we then take a charge capacitor and effectively connect it to this point here and bolt it on, so we get this kind of configuration, we will end up with doubling of the voltage at the output, because the voltage on here is maintained. Just like the inductor tried to maintain the current, the capacitance will try and maintain its voltage. But I always think that it's a lot more intuitive with voltage driven systems. So if we break this connection here and take this capacitor and stick it on here, then we've got a potential difference of 2 volts across the two. So we double the voltage. But as soon as you start to take current out of this system, then the voltage will start to fall, because there's a finite supply of energy stored in these capacitors. So what you then do is you then reconnect it back onto the power supply, charge them up again, and then switch them back to this to get our 2 volts. And hopefully the load hasn't noticed it's been disconnected. And there are ways of trying to make that be as smooth as possible. So we can use switches. We can maybe use diodes like we did before, but that's fundamentally the kind of idea that we're going to be pushing here. Charge them up in parallel, switch them into series, and it's clever ways of doing that that dictate how this happens. So what have we got? So if we can use switches or we can use diodes, and here's an example of a circuit that will allow us to step up a voltage. So we're driving it with a frequency here, which is just switching this capacitance here. That's a switching thing going on, and this voltage here, with any luck, gets doubled at this point here. So let's see what's going on. Hopefully the next slide will tell us a little bit. So some assumptions for the purposes of analysis anyway. No load is taken from Vout2 and everything is ideal. So here's Vout2, nothing is coming out of here, and everything, diodes are ideal, and everything else is ideal. So when the frequency, in this case a square wave, is low, so when the duty cycle of the square wave is low, just pull a pen. So okay, when we're down here, at this point here, then current can flow through this diode and charge up this capacitor. And then when frequency goes high, and then let's assume it goes to 10 volts, so it's a 10 volt square wave, when that goes high, the voltage will be maintained across this capacitance. So remember, it's charged up to 10 volts when this was at 0, because I've got a 10 volt supply in it. We then switch this point to 10 volts, and this point will go 10 volts higher to maintain the 10 volts that across it in the first place. And so that goes to 20 volts then. That then forward biases this diode, and so this one will start to charge up, and eventually we'll reach 20 volts ideally, but of course there will be a drop if we think about this, as this one is not going, but we'll look at the simulations for that. So this is just a sort of a first order approximation in principle. And then the whole cycle then repeats itself, and then eventually C2, this one over here, ends up with 20 volts across it. Remember, we're not taking any load out of it at the moment, so it should eventually step itself up and sit at 20 volts, given there was 10 volts coming in and we've just been switching a 10 volt supply here. And so that's quite a sort of a neat trick. And it says that with a bit of imagination, it is quite a lot of imagination actually, we can think of C1 and C2 switching parallel to series through these diode switches, but it's quite a loose analogy. The best thing is just to think about what's going on, get an idea for what's going on. You can see that this whole thing is moving upwards in terms of voltage and dumping some voltage into this one, and then when this one drops down again, the voltage can't, or the current can't escape through this diode because it's reverse biased, so it's maintained here. So we end up with a reference that we can compare against. But you can see how it sort of pumps. It says there's sort of a pumping effect going on. Let's go back to a pointer. So there's a sort of a pumping effect going on at this point, and it's all being stored in this thing. So when you turn it on from nothing, with the square wave going in, you can see that the sort of frequency of the square wave imposed on this, and you can see that it charges up quite nicely in the simulator and gets to 18.9 volts in 1 millisecond with I think it's probably a 10 kilohertz frequency driving it. Okay, we're expecting 20, but this is the real world, remember, and we've got some diodes, so will be some diode drops included in this. And there are and that's where we go. So this technique can actually be extended, and we can just add as many of these stages on as we really wanted to, and exactly the same kind of thing happens. So we've just multiplied, we've got another stage here, and we just bolted on another stage here, being driven by the same frequency, the same system here, and this adds another 10 volts to our output. So you can see, and here we are, you can see that the one is getting itself to 18 volts or 19 volts or so, and the other one is ramping itself up to, well, we're close to another 10 volts on top of that, so getting close to 30. If those diodes were ideal, we would be getting 30 out. So we've gone 10, 20, 30 in 3 stages. And you can keep on adding stages to this kind of system, and you can get very, very high voltages. And as long as you don't take very much current out, it's all great. But if we add a load, and as we start to take some useful current out of this, we will start to introduce a ripple voltage into this point here. So let's add a 1K resistor load onto the output to do something useful and see what happens. And now you can see that we're starting to generate a ripple, because each one of these little spikes here is when our load is taking current, so it falls and then it gets recharged again, and then a bit of current is taken. So you can see how lumps of charge effectively are being pumped through this system and then being used in the load. So a ripple is starting to appear. The size of the ripple is dependent on the switching rate. Obviously we can see that if we switch much faster, the size of that ripple will go away. It's also dependent on the value of the load resistance, and it's also dependent on the size of the capacitances, so that dictates how much charge can be pumped through this in one cycle. So as we take the current, the voltage drops, so we just need to think of ways of mitigating and minimizing this. It's never going to go away completely. But we also had ripples in the inductive systems as well. So again, it's just a question of understanding the system and adjusting accordingly. So we can play around in the simulator. So we've gone up in frequency 10 times, and the ripple now is much less, but it takes longer to pump up. Oh, I don't think that was right, was it? What's going on there then? Okay, alright, so 10 times bigger in terms of the output capacitance, that's right. So we've gone to bigger capacitances. Obviously it takes longer to charge up the capacitances, then this is making a lot more sense. So it's taking much longer to charge up, but we get less ripple because there's more charge available to drive our load, which hasn't changed. So if you go up in frequency, now all of a sudden everything is looking quite nice. It's getting up to speed relatively quickly, and then it's stabilizing. At this scale we can hardly see any kind of ripple on this thing at all. Obviously we get the ripple back if we took out more current. So you can see that this is quite an elegant system in many ways. But because we're dealing voltages, it becomes we can play with other configurations as well. And so this system here actually allows us to generate a negative voltage rail, and you can see it's actually quite a simple thing with a couple of diodes, again a storage capacitor, another capacitor, and driving it with a square wave. So assuming that frequency is a 10 volt square wave, we end up with the same kind of pumping thing, but we're switching it slightly differently now. So when frequency goes high, C5 charges up. Okay, so that goes high, we charge up through this system, so this ends up at 10 volts or so. When frequency goes low, C5 maintains the voltage across itself, and so the anode of D5 goes to minus 10 volts, which is here. Okay, so we've still got to have the right number of volts across this capacitor here. That leads to C6 starting to charge, because current can go this way, because this is negative with respect to this, so this one charges up, and we'll end up with effectively the negative voltage of minus 10 across here. And then we repeat the cycle again, but it pumps it, and it leads to a negative charge pumping effect, because we're generating a minus voltage across the output capacitor. So if you look at the switching forms in this system here, the interesting one is the red line, which is the output voltage of this thing, which you can see is now going down to, in an ideal world, minus 10 volts, but not quite there because of the diodes, and we have to have a diode drop because the diodes are conducting, so they'll have 0.6, 0.7, 0.8 volt across them, depending on how hard they're conducting. So quite neat to get a negative supply from just a positive switching supply. I hope you'll agree. And again, we can cascade stages. Believe it or not, this is a cascade of these stages. It's all about which way around the diodes are, really. And we can cascade these to create larger negative voltages. The only subtlety about this system is there is no DC positive power supply needed in this system. The only input we've got into this system is this square wave. So this is the thing that's actually providing us with energy or power. So it needs to be able to supply us with significant currents. So although you can use sort of just a signal generator, signal generators tend to be not configured for supplying a large amount of current. They'll only supply, a few milliamps or so. So as long as you've just made a small system, that doesn't require much output, that's great. But if you want to start putting serious amounts of current through this frequency generator needs to be able to supply you with a significant amount of current, or certainly enough for your purposes, because you're powering it off this. This is the only source in the system. Okay, so don't think that you can get infinite amounts of energy out of just running this off a 555 timer or a benchtop signal generator, because that just won't happen. So that's one of the limitations here. But as long as if you design a frequency source that has a low output impedance, so it can drive currents quickly, so it can charge these capacitors easily and fast, then it all works. And you can see you can keep cascading these stages, and here we're getting close to minus 20 volts on this. So they're quite simple. It's just a few diodes and a few capacitances and a signal source. So I think that's quite elegant sort of system, really. And I found this this is quite a nice data sheet. If you look at this, there's nice pictures in there. A lot of this stuff's not very well covered out on the web. It's one of these subjects that people just don't seem to want to get into. But this is a nice diagram that shows the similarities between the step up and the inversion. Step down, well, not step down, it's just invert step up systems, and you can see that they're remarkably similar except for the direction of the diodes in the two types of circuit. So this diodes this way give you minus voltages, diodes this way give you positive voltages. And it's only on this sort of input connection that things change. On the negative one we're connecting a diode to ground, and on the positive one we're connecting the diode to a positive supply. Okay, all good, all quite interesting and useful. So the requirement for a separate power supply, because it'd be quite nice to be able to get positive voltages from just a frequency supply and not have to worry about having a frequency voltage to drive with. We can get rid of that if we can just think of a similar way of driving this circuit as we did for the inverting circuit, but using, just for the sake of argument, a signal generator. And this would make the system behave in a similar way to a transformer, in that AC voltages can be transformed to higher level without any active devices or power supplies. The difference being, of course, that in this case we put an AC in, it gets converted to a higher voltage, but comes out as DC. So we've got an AC to DC conversion implicit in this type of system. So it's a sort of a combined transformer and rectifier in one. And we use this a lot in Thames Group because we tend to try and power things from energy in the environment, and most energy in the environment that we're interested in, because it's industrial environments that are interesting, tends to be vibration. So if we can just turn vibration into electrical energy, we can then power all kinds of nice systems. And this is a really elegant way of doing it, because the vibration itself becomes the thing that drives the system. It gives us our frequency source, and we don't need any batteries or anything in the system to start it up. In fact, excuse me, we've just spun out a company that's based on exactly this technology. As I spun it out, we spun it out a few years ago, and it's just now been sold to Hitachi, and it's a system that takes vibration from railway carriages and turns that into power, and then measures the vibration in the bearings of trains to monitor the performance of train bearings, so that you can decide when to replace them and when not to replace them. You don't want your train breaking down on the railway track, because it blocks the track for everyone and gets expensive very quickly. So if you know when your bearings are failing, then you can obviously plan your maintenance. So this is a excuse me, powering a whole new area. It's all this information about the bearings then goes into sort of artificial intelligence systems that makes predictions about the future. But all that artificial intelligence stuff can only make good decisions based on the good data coming in the first place. And what it needs is information about how the bearings are running, which is measured by vibration as well. So that's all quite useful. But you might say, well, why don't you just power things from the power supply in the trains in this particular case, which is in fact what we said at the beginning. And there are two reasons for this. First reason is that goods wagons don't actually have any power in them at all, which was a surprise to me, and there are a lot of goods wagons around. And secondly, on passenger trains where there is power, any kind of system that connects into that power supply has to be guaranteed to be absolutely safe, because railways are paranoid about safety, and that takes years to pass all the tests, and loads and loads of money, millions of pounds, to actually allow anyone to plug anything in to the electrical systems of trains. And even the train engineers don't want to do that. So when we turned up with something that was self-powered, that you just bolted onto the outside of the train, it didn't connect to electrical systems, they said this is great. And it's just been sold into the open market now, so that's quite good. So all these little systems can actually become quite useful, and it's all about imagination and how you can apply them. And you can see how the basic idea of just two capacitors, one being pumped up, is sort of being developed into new and interesting ideas. So there's a description of how that works there, and basically it's just another switching circuit. But we've effectively mirrored the inverting circuit again, and we've said there's no need for a power supply. We'll just take it all from the frequency generators. So if you're interested in how that works, then the best thing to do is to sit down and just follow the voltages through, create the little graphs, and spot what's going on. But there's these things start up slowly, and as we saw, if we just ping back to this graph here, you can see when it started up, it didn't start up straight away. There was a timing, a period of time where the voltages were starting to rise before it stabilized out, and that's what this part of the system is looking at here. Just ping back to that. So I don't think, do we really need to go through it all? Well, anyway, let's go through it. So consider capacitor C charged up to V, so Q equals CV, that's the charge on the capacitor. When it's connected in series with another capacitor that is uncharged, the charge will balance across both capacitors. So if you have two capacitors in parallel, and you have one capacitor, you charge it up, you put another one in parallel with it, the charge will balance, and you'll end up with V over 2 on each capacitor. And that's what's going on in these charging circuits. The first, because we're switching capacitances in, the first one reaches a voltage, and then we switch in the second one in parallel with it, and that will go to half the voltage, and then that holds that voltage while the other one is then charged up again, and it keeps just pumping it through. And so you can see then that eventually the final capacitance will be holding the final voltage, and this is just showing it, stepping you through each of those cycles on that graph I just showed you, allowing you to get an idea of how quickly these things can charge up. And you can see in principle it never quite gets to the final voltage. It's one of these sort of exponential things, but that's just an explanation of how that happens. And then, because we've got diodes in this system, we will have to allow for 3 diode drops in our system to predict our total voltage at the output. So it's going to be whatever the theoretical voltage would be, which we said was maybe 20 volts, but we're going to drop 3 voltage drops across here. So you can see why that the estimated 20 or the expected 20 volts is actually a bit less in this case here. So these are using signal diodes, silicon diodes. There's another type of diode called a Schottky diode, which is much simpler, has a bit more leakage behind it, but has a much lower forward voltage on it because of the nature of the PN junction. So they'd only have about a 0.3 volt forward drop across them. So they're a better idea if you want to get maximum efficiency in terms of voltage generation. So if you replace these with Schottky diodes, you will get much closer to your 20 volts. So you can see how these things work. This type of circuit was originally invented for generating really high voltages. You see 700 kilovolts was generated from such a system, and it was used to smash atoms for the first time, because if you accelerate protons through a very high voltage like that, they go very fast, and it gives them lots of energy. And when they actually happen to hit an atom, chances are they'll knock it into bits. And it was called the Walton-Cockcroft circuit, and as I say, went to 700 kilovolts or so, which is lots of volts. Don't want to get near that. Not much current though. That's the interesting thing. Right, so that leads us nicely onto switch capacitance. So there's a bit of a caveat here. It's important to notice that this is a basic introduction to switch capacitors, because we haven't got very long. And it's fundamentally a sampled data system that the sampling techniques such as Z transforms can be used to accurately model them. So I'm not expecting you to have done Z transforms. You might well have done them in signal processing courses. We will do a little bit more on Z transforms when we come and look at A to D converters, but I'll only tell you what you need to know about them, not all the details of it, so so you get the general idea. So don't worry too much if you don't know what a Z transform is. Right, with that caveat out of the way then, we can look at it at a high level. It is possible to simulate a resistor with a capacitor. So here's a capacitor, and here are 2 switches. So I've put them in as FETs, transistors, but they could equally well be switches of any kind. And we're saying that this system, and these are being switched on and off, these switches, can be the equivalent of this, which is a resistor. Okay, so it'll be effectively anywhere you see a resistor on a circuit, you can replace it with this in some shape or form. So we're emulating a resistor with a capacitor and a couple of switches, and this is important in many ways because integrated circuits are very good at implementing switches, and it turns out they're also quite good at implementing capacitors, but they're not very good at implementing resistors. So this is part of the drive behind this. We don't want to integrate resistors, and we certainly don't want to integrate large values of resistance. So this allows us to actually do away with resistors and replace it all with capacitances and FETs or switches. So C1, T, and C2 are two clock signals, so they're just bouncing up and down. J1 and J2 are two MOSFET switches, so they're just transistors, and Q equals CV for the capacitance. And so the charge stored on the capacitor depends on the value of the capacitance and the voltage across it, effectively. So the only assumption we have to make is that the clocks are non-overlapping. Okay, so that means that then these switches are never opened at the same time. There's no path through this system. So the capacitor is charged repeatedly to V1 and V2 as the clock switches. So it's charging with this clock on, this switch on, this switch off. It'll charge up here, and likewise with this one on, this one off, it'll charge to whatever this voltage is. So voltage may come out, or current may come out, or it may go in, but it's going to maintain it. So we end up then effectively with this being an average voltage between these two. Therefore, there's an average change in charge over the clock period, which is called delta Q1, if you like, equals C1, and the difference in the voltage. So that's the change that's going on. And this will then lead to an average current over time, because charge, current is a moving charge. And so if we do this over time, we end up with a current, average current, which is whatever the change in charge was, C1 V1 minus V2, over T, which is the clock period, it's time going forward. Okay, so we can relate this to Ohm's law, and referring to the resistance diagram in above, then I average is equal to V1 minus V2, which is this bit here, over an equivalent resistance, which we can see is going to be what's left of this equation. So C1 over T must be the equivalent dimensions of a resistance. And so by equating these two equations to each other, well, we can see that R equivalent is equal to T over C1. Where T is the period of the clock that's driving these switches. Or alternatively, if we say that T is 1 over the switching frequency, 1 over C1 Fs, the switching frequency. So the value of this equivalent resistance in this circuit is controlled by the frequency of the clock driving this. So if we change the frequency of the clock driving this, we can change the value of the resistance between these points. The clock has to be very, very fast compared with the signal that we're trying to drive through here in the first place, as always with these things. And that's quite neat, because as you'll find out when Kay Lee takes over after Easter, he'll give you all kinds of interesting ways of generating variable frequency clocks with voltage controlled oscillators and phase lock loops and things like that. So all this starts to all link up at that point. So this shows that a discrete time system, so that's a switching system, discrete time is a switching time system, can emulate a resistor, and that obviously becomes quite a powerful technique. So for example, here's what we will now recognize as a integrator circuit, which we're starting to realize are actually quite important in terms of filters and PWM and all that other kind of stuff. A switched equivalent of that is just this, where we replace the resistor with two switches and a capacitor, and then the time constant of this now is now going to be controlled, RC is going to be controlled by the frequency that we're driving this at here. So we can make a tunable filter, if you like, made of variable resistance. Okay, so non-overlapping clock is important, because there must be no way that the charge on the capacitor can be removed. We want it to, between switches, it needs to be static in here. If clocks that are very close in time are used, it is possible that delays in switching will result in both switches being conducting at the same time, because there might be a delay in the switching because of how it's constructed. And if you get that, then you start to get errors in this, because the charge that you're expecting on here has managed to escape a little bit. So the quality of the switch is important. So designing a switch here, there's a whole area in electronics of designing switches that are really, really efficient, because any kind of transistor will have a junction, and any kind of junction will be able to store charge, and that results in something called charge injection. As this thing switches, the charge in the junction has to go somewhere, and sometimes it gets injected into the system you're interested in. So there are all kinds of clever ways of designing switches that try to minimize that effect and other effects, so that we've got the ideal perfect switch. And there's a lot of effort goes in, as I said, into designing for that. But IC designers don't mind about that so much, because transistors are cheap. So even if this switch is made up of a whole bunch of transistors all switching cleverly, it doesn't really matter as far as they're concerned, because it takes up very little room on the device, and they're very easy to make because you just make everything at the same time in an IC. Right, so given what we know about the equivalent resistor now, we can calculate an equivalent time constant. So the time constant of an integrator is RC, as I just mentioned, which is R equivalent C1, which is now dependent on T, and that's 1 over F. Thus the time constant determines the frequency response to the circuit, and that's defined by the clock period T, and in fact the capacitor ratio. And that's the important part here as well. It's not the absolute values of these capacitances that are important, it's the ratio. And it turns out that making accurate capacitor values in ICs is tricky. So making an absolute value of capacitor is tricky, but making accurate ratios of capacitors is really easy, because it's just defined by area ratios. And so the quality of the dielectric in between, as long as it's the same on the same piece of silicon, is not important. It's just to do with areas, and defining areas on ICs is dead easy. It's what it's all about. So ratios are easily controlled to within 0.1% or so, and you can also make capacitances that are quite small, giving very high time constants, very fast oscillators. So 0.1 picofarad is a sort of a reasonable value of capacitance that can be integrated. Bigger as well, but this makes everything work very fast, which is quite good. And as I say, here it works out very well for audio in particular. With ratios of 10, and so we can get switching frequencies of 100 kilohertz or so, which gives us nice reasonable time constants to play with in sort of audio filters, things like that. And the higher in frequency you can go, the better, so this kind of small value of capacitance tends to be very useful there. So just to give some idea of simple extensions, I say simple, it's still not that simple, which allow you to go a little bit further. There are implementations of the systems here which are insensitive to stray capacitances, because there's always going to be little capacitances in the layouts. You know, you might find that even when you design things properly, you're always going to get possibly little stray capacitances going to ground anywhere, you know, even down through here. Everywhere when you're starting to deal with small scale capacitances, there are going to be little strays that start to become significant compared with the size of the things that you're interested in. If this was a huge capacitance in the microfarads, then you know, a few femtofarads of stray capacitance here is not going to make a lot of difference. But when these start to become similar to each other, it becomes important to worry about these kind of things. So people spend a lot of time then trying to design systems where these strays become insignificant, or at least can be got rid of. So we're implementing slightly more complicated switching arrangements here, and this isn't really part of the course in terms of it's not going to crop up in exams or anything. The importance of what's going on in here. I'm just trying to open people's eyes to the fact that there are a lot of little tricks that people can use who have studied this for a long time to try and minimize the effects of these systems. So won't worry too much about that. So implementations of complex systems can be as straightforward as taking the continuous time architecture. So this is very similar, if not the same as, the Tau-Thomas architecture for a certain filter. Looks like looks like a second order low pass, Butterworth or something. And just replace the resistances in this with switch capacitance equivalents shown in this system. So this resistance here has just been replaced by this block, and you can replace this block with any block of your choice for an equivalent switching capacitance with complicated switches or less complicated switches, depending on who's done the hard work on designing that block. And you can see the block here is all plugged in, and the block here for another resistor. So all these resistors have just been replaced. And the nice thing about this is they're all being driven by the same clocks. So all these are being driven by the same. You have one oscillator generating the clock phases, so the out of phase clock phases, and you just feed them to the right inputs on these transistors, and so everything is then controlled by one clock. So the overall accuracy of the frequency cutoff of this system as a filter is now pretty much defined by the accuracy of the clock that is being used to generate the switching frequencies for this. So you can put all your time and effort into making a really, really good, highly accurate clock, and the rest of all this stuff will just follow accordingly. Everything is synchronous. It's quite nice. So you can see how these ideas are starting to come together now. So some examples of switch capacitance ICs, which quickly, I'm hoping to finish this today. There's some chips out there. The LTC1043 is a really interesting device. It's really just a chip that's got loads of very good switches in it. So you can actually buy, people have designed some switches that are really good, and you can just buy them in integrated form. So you can use these switches as the basis of any kind of switch capacitance system, and you just provide your own capacitances. So this capacitance is not in the device. This capacitance is connected to pins 11 and 12 of this chip, and this allows you to make all kinds of interesting things. So you can see here, this is literally just switching the value of this capacitance and pumping it into this capacitance here. With the switches to the left, as set up here, the two 1 microfarad capacitors are in series with each other, and you can sort of see that. So there's one there, and this one is connected via this wire to that end, and yeah, and they're all connected in there and connected through ground. So we've got that. Each capacitor, when you switch to V in at this point here, each capacitor will end up with V in on each of the two capacitances. Because they're in series, we end up with half that voltage across each. And when the switch moves to the right, the two capacitances end up in parallel. Yeah, okay, so they're in parallel, each with V in across them, so they add up. So this is literally the first slide we looked at. It's taking the two capacitances, charging them in parallel, and then charging them up in series, and then dumping them in parallel. Okay, so that allows us to make a very accurate divide by 2 circuit in terms of voltage. So whatever the input voltage is coming in here, we will end up with the output voltage being half of it. We can do the same with the multiply by 2, just by rewiring it a little bit. With the switches to the right, the center capacitor will charge up to V in. Is that right? So we switch to the right there. Yes, because we've got V in over here now. So that will charge up through there. When it switches to the left, the output becomes V in plus V in, because pin 13, the bottom left, this one here, is permanently connected to V in. Yes, it is, through that wire there. And the switch capacitor itself has a difference of V in across it, which will add itself to the pin of V in. So we end up with a charge pump giving us 2 V in. So we do need an output capacitor on this, which allows us to just hold that voltage while a load is actually taken out. So you can see, just by changing a small connection within this chip, we've now got something that was halved and is now doubling. And the same kind of idea allows us to generate a negative voltage from the same chip as well. A small change in configuration allows a voltage inverter, and you can just follow the voltage through again. V in comes in here, and then it gets switched, and because we've effectively swapped the grounds over on this system, the voltage polarity on this one in the middle is flipped over, and so that gives us a negative supply. So this becomes quite a useful little chip, really. And this is a really neat little circuit. This allows us to make an instrumentation amplifier, which we covered earlier in the course, from one op-amp and a switching circuit. So the fundamental function of a single set of switches is as a differential to single-ended converter, because the voltage across this capacitor, the switch capacitor, is maintained relative to the either end. So suddenly we can boost this voltage to a reference level of anything we really like. So if we feed a differential signal in here and sample it, because that's what we're doing really, we're just sampling the differential voltage across here, and then we switch it to this point here. This end is now fixed at ground, and this end will move itself to be whatever the differential voltage was away from ground. So we've gone from a differential signal, by just measuring the difference, to now a fixed single-ended output. And then we can just amplify that. And any common mode signals, so the same voltage appearing on both these pins, it's just got rid of, because we're sampling the difference voltage. The common mode is irrelevant because it's effectively floating, and it's switched to a new reference when it switches over. So this is actually really, really neat. So the important thing is that any common mode signal at the input is not transferred through the capacitance, and this whole thing becomes frequency independent. Remember, the common mode rejection ratio of op-amps was very, very heavily dependent on the input frequency and how good the gain of the op-amp was. This is only dependent on the switching frequency in terms of the common mode rejection, because all the common mode rejection occurs in here. This hasn't got anything to do with it really. So that's quite nice. So there's a little note at the bottom that says this simple system requires a plus-minus supply to operate. But remember, if we've used this chip, we've only used half of the LTC1043, we can use the other half with the other switches to generate a negative supply rail. So we can then power it from the other half of this chip. So it makes a very neat little system here. So really good. Now I would say to you, take an interest in how this operates, because it's not unknown for this to crop up in exams. It's a little bit, because it's such a neat idea, and it encapsulates lots of other concepts from elsewhere in the course. So although we go over it very quickly at the end of a lecture, in this case, it's probably quite important to you. And there's some other, just finish this off with a few other devices. You can buy an LMC7660, which is quite common, and it just generates a negative potential. If you want to generate a negative supply, buy one of these chips, plug it into your circuit, and it gives you a negative supply. Just need to check the current requirements of it though. And then people have actually made life really easy for people by making blocks of switches that give you 2 second order stages in a system, so you can actually build filters really easily, like the Tau Thomas. So it's all in here, and all we do is control the cutoff frequency by changing the clock frequency of the that's driving into this chip here. And in fact, usually the clock is defined internally as well, and you just control it by a resistance. So you can feed a clock into here, for example 1 megahertz or so, and that dictates the cutoff frequency of the systems that can then be designed. And all you do is tweak these resistances a bit on the outside to give you what you want. Refer to the data sheets for more detail on this kind of thing. But then it starts to get really interesting, because Maxim in particular have taken this thing to heart, and you can buy things like this Max 291, which is an 8th order Butterworth filter, all ready to go. So they've done everything in there, and all you've really got to do is provide it with a clock, and the input signal you feed in here will then be filtered depending on what cutoff frequency you programmed in with the clock. So here's a one design for 1 kilohertz, and you can see that it all falls away really quickly, and all you've got to do is put in a high frequency clock into the thing. So you can actually tune between 0.1 and 25 kilohertz, which is the audio range. So you can actually cut off with an 8th order filter, which is close to the ear's response, as it turns out, and it's just controlled by an external clock. So you know, you get some idea of what's in these chips now, and where the limits may lie, but we just need to know they're out there. Right, so that's the end of that part. So we've overrun by 5 minutes. Sorry about that. And we'll pick up next week on power amplifiers and move forward to later on to digital and analog converters. Okay, thank you.